Hello and welcome back to Calculus 2, section 11.2 on properties and convergence of power series. There is a little part in the book talking about derivatives and integrals of power series. I'm going to kick that out into 11.4, which is the next lecture. So don't worry about that for about, one class, which is a week for you. But anyway, so what do I have? The properties first. So we're going to go in order here. And I just want to bring something. When we talk about the convergence of power series, it's not the same as talking about the convergence of series. Are you using the same tests? Basically, you're using ratio tests. But over there, convergence is convergence, divergence is divergence, and that's it. I want you to think a little bit about, kick the ck out. Just think of x to the n from 0 to infinity. Like, where does this fall? Geometric, right? So would you say that this converges or diverges by geometric?
Can't tell without knowing what x is.
Exactly. This converges and diverges, just like Schrodinger's cat, right? It converges and diverges until you actually measure it, right? Until you look at it. You see, if you look at this and you say, oh, geometric series test, I will agree with you 100%. But see, the trick is that this x restricts on, right? So when you have this summation xn, it branches into two different worlds. For x between -1 and 1, we have a convergence. And then if absolute x is bigger or equal than 1, we have divergence. These are exactly the conditions for, right? So power series converge and diverge at the same time until you figure out which x you're talking about. Which is why we have interval and radius of convergence. So we are introducing now interval and radius of convergence. So for the problem up there, for summation x to the n, interval of convergence is -1 to 1. So any x you pick between -1 and 1 will make the power series converge. Let's write that in orange, I guess. Any x we pick between -1 and 1 will make power series converge. It's called interval of convergence. Clearly, it should be a list of numbers or of x values for which the power series or the series converge. Now, do you see that when you pick a value, power series becomes regular series? What is this? Power series has x, regular series has no x. So if you pick that x is 1/3, then this becomes regular geometric series and it converges. If you pick 7, then your power series becomes regular geometric series that diverges because R is 7, right? So interval of convergence is just this range for x, right? And you pick anything from there, it makes it converge. Pick anything outside of that interval, it diverge. Radius is a half of this. Radius is half of the interval. Radius of converge is half of interval. And in this case, for our problem, for summation xn, radius of convergence is equal to 1, because that's half of my interval. Now, you might challenge, why is called the radius if we are on the x-axis, right? It makes no sense. No, it's for complex numbers and Lorentz series, actually. When I'm going to delete this, you have the real axis, you have the imaginary axis. The power series look like that all over the place. And then when you find the convergence, it has some kind of radius to it. Now, since we are only on real axis, still the same radius would apply, except there is nowhere for it to go in space. So we still call it radius of convergence. But it's because later math.
I have a question about so is the power series it's only the interval of convergence, and then like when you're outside of that interval it's just a regular series?
No, it's both, actually. So here, let's just clear that up real quick. So if I have my power series to be x to the n, this is called power series. Power series, and I say has x in it. Now, pick x equals 1/3. Well, then your power series becomes regular series, because now you have 1/3 to the n, and that becomes geometric series, which converges. If you pick, I said 7, then you have summation 7 to the n, from 0 to infinity, geometric series, which diverges. Here's another example. Say your power series is x factorial. To the n. So that's power series. It's not, this power series here is not Taylor. It's not polynomials, right? So now, oh, I can't do it this way. I want to use factorial. X over n, x to the n. Can I do x to the n like this? Yeah, let's do this. X to the n factorial. So that's power series because it has x in it, right? Now you pick, let's say x equals 1/9. Then you get summation 1 to infinity of 1/9 factorial. Pick x equals 3, you get summation of 3 factorial. No, 3 to the n. Factorial. Literally anything you write that has x, you can. Now these are all, this is obscure example, whatever. It's just for us to understand that once the x is picked, you are leaving the realm of power series and you're going back into chapter 10. Now we're never picking those x's because we actually want it to be an x so we can match it to a function. But if you are to pick an x, you immediately reduce your power series down to a regular series and you just use the sheet to check for convergence and divergence. Okay, now here's the big sentence. Convergence of power series is checked by ratio test, in parentheses, sometimes root test, sometimes. Ratio test is your god over here. So we're going to take a look at 3 power series and understand the way they work. So I have to find those examples. Let's go with x to the k, x to the n. I don't know. I hate k. K is hard. Look, to write n, you do this. To write k, you have to. It's yeah. So n 0 to infinity, x to the n over n factorial. What are the interval and radius of convergence? All right. The answer here is use ratio test, sometimes root. Use ratio test. Okay, cool. You know the drill. Your an is x to the n over n factorial. Your an plus 1 is x to the n plus 1 divided by n plus 1 factorial. Your limit, n goes to infinity. Holy nightmare. If you forget absolute values here, your problem is done. It's not minus 1, it's not minus 2, right? Its problem is gone completely. Absolute values must be here. They are part of calculation. The rest of the ratio test goes the same. We peel off an x, we have x to the n. Peel off n plus 1, we have n factorial times n factorial over x to the n. It's a factorial here, it looks ugly. Go. Absolute values still. Kill off factorials, kill off x to the n, and you are left with a limit n goes to infinity of absolute x over n plus 1. Now, do we all understand that limit is n goes to infinity? X has nothing to do with this. We also understand that n are counting numbers that are always positive. X can be anything, right? But the n's are only positive. So this absolute value bothers x alone. It doesn't bother n plus 1 at all. Also, limit doesn't bother x. It bothers n plus 1. So because of that, I can kick absolute x in front of the limit, because in the eyes of the limit, this absolute value of x is a constant. Limit operates on n. Limit operates on n. And this limit is 0. We just got that the ratio test told us that this mess is less than 1. What do we know because of this? Converges for all values of x. Right? It's this thing that killed it. Right? Your x could be negative half, it could be positive half, it could be 7, could be pi, it could be 1 million. When you multiply that with a 0, right, it will always die. So, always true, because 0 will always be less, which means interval of convergence is negative infinity to infinity, and radius of convergence is r equal infinity, which is the half of infinity. Cool beans. This power series converges everywhere, regardless what x you pick. Now, when you go up there and you realize that you have exponential divided by the factorial, and you know that factorial is the boss, right? Then, yeah, it makes sense. Cool. Next example. A bit trickier. No reason to panic. We have negative 1 to the n, x minus 2 to the n, divided by 4 to the n. What is the one feature of the piece of the power series that you can tell me right away? It's alternating, okay. What else? The other power series? Centered on 2. I need you to develop that skill instantly when you look at the problem centered at 2. So I'll write it in blood. This PS power series is centered at 2. You will see why is really, really good to know that the instant you look at the problem, you recognize that. You will see that at the end of the problem. Let's go and just do our ratio test. So now we want to know again what is the interval and radius of convergence. That's the question, right? What we care about. All right, cool. Remember, when you do ratio, there will be absolute values. It's going to kill the alternation. I don't even have to bother with it. So my an is just x minus 2 to the n over 4 to the n. And my an plus 1 is x minus 2 n plus 1 over 4 to the n plus 1. I am not bothering myself with the alternation term. Absolute value will kill it, right? Alternation term is either 1 or a negative 1. You apply absolute values to it, they're all 1s. So, gone. What do I have? Limit n goes to infinity, absolute value. We peel off x minus 2. We still have x minus 2 to the n. So that's n plus 1. When you peel off the plus 1, that's extra parenthesis. Peel off a 4, still have 4 to the n, times the flip of the original problem. Close absolute values. This is cool because this one dies, color-coded, canceling there. And we are left with the limit n goes to infinity of absolute value x minus 2 over 4. The hell, there are no ends. So what's the limit? There's no ends. There's nowhere to plug infinity. So it's just this. Right? That's it. Now, what do you want from this problem? You want convergence, right? When does the ratio test converge? No, ratio test converges just less than 1. Guys, you are the ones who set this less than 1 because you want convergence. I'm going to write this here. We set this less than 1 because we want convergence.
As long as x is less than 6, you just solve it like.
Now it's algebra 1 problem to solve inequality. You need to know what it means to have these absolute values. You see that? That's why they're important. It kills your interval if you don't have them. Your interval is 2 numbers. This one, right? So now, going back to algebra, x minus 2 over 4, the 1 in algebra means negative 1 less than x minus 2 to the 4 less than 1. Do we all see? If you don't have absolute values, you don't get to put this, and then you don't have the left part of your interval, and your problem is gone. Right? So it's not minus 1 bad notation, right? It's minus 10. You have no interval. You didn't answer anything. So absolute values in the ratio test must be there primarily for this purpose, right? So now multiply by 4 everywhere. So that's going to be negative 4 less than x minus 2 less than 4. And then add 2 everywhere. Negative 2 less than x less than 6. What is your interval of convergence? Well, that one. So your interval of convergence is negative 2 to 6. That means if you pick any number between negative 2 and 6 for your x and stuff it in a power series, replace that x with a number, then your power series will become convergent geometric series. What's the radius here?
4.
Wait, no, he was right. I'm just kidding.
What?
Nothing. Don't worry.
I didn't hear. So radius is 4. And if you want to think a little bit about this, right, you can put it on a number line. Here's your 0. Here's your 1, negative 2. 1, 2, 3, 4, 5, 6. Do we see that there are, this is your interval of convergence, right, from 2 to 6. Are we all bueno on that? So do we see that the interval is 8 long? So radius, half a diameter. Good. So radius is 4. Awesome. Can you tell me anything about the center of the circle? And why is that significant?
Because the beginning of the problem said it was at 2.
Because the beginning of the problem said that our problem was centered at 2.
So is that just a way to double check that you didn't?
That's the way to double check that you don't have a ridiculous answer, yes.
So if we weren't centered at 2, that means we did the entire thing wrong.
Exactly. If you go all the way to the end of the problem, you come up with a radius of convergence that doesn't include 2. I mean, come on. The problem is centered at 2. It must be in the middle of the problem. If the problem is centered at 0, 0 has to be the middle of the interval. First example had negative infinity, positive infinity, so you can't really tell, right? But for this problem, it's a perfect example. This is the best example of the entire section. Because you start by noticing that the problem is centered at 2, And then you finish your problem, you calculate all of these things. This is your answer that you present for your full credit. But then you think a little bit in the background and you say, holy, right? Look at that. It's right there. It's the middle. Awesome. So hopefully that will sync, right? And you guys will have one more example.
Professor,
Yes.
in the My Math Lab, can you extend chapter 10 and 11?
Yes. So now we have one more example, which is summation 1. And now we're going to have n factorial times x to the n. And I will let you do the ratio on this one. You already know an is n factorial x to the n. An plus 1 equals, divide them. Don't forget absolute. Do we all have the same setup? So I hope that you were all able to get here.
Why doesn't the n plus 1 stay in? Well, it wouldn't matter for this problem, but would that also stay in?
It never matters.
Okay.
Because n is always counting numbers and they're always positive. So absolute value has no bearing on n plus 1 or anything like that. Now, what do we know about the limit of n plus 1?
It's infinity.
It's infinity, right? Now, that would be bigger than 1. Is there a way to make this smaller than 1? If?
No. Not the way it is written there.
How about if x is equal to 0? Yeah, that makes everything 0, right? Yep. So, this is equal to absolute value of x times infinity And the only way to make this less than 1 is if x equals 0. So, if x equals 0, we have convergence. Otherwise, divergence. Such is life. So, we say that this power series converges at the point with the radius of convergence 0, obviously, because there's no, right? So right here we'll say this power series converges at a point with radius equal 0 because, right, nothing else converges. So there is no interval, right? It's a single point for convergence. Does it have to be 0? No, your problem might be shifted and then it's going to be 2 minus 2 is, right? So I wish that this was a shifted problem. I mean, I could have reworked it as a shifted problem, but this problem is centered at 0 and it's only at that point that it converges. The rest of it, it's divergent. Do we want divergent series, divergent problems in our engineering? No. They're all unbounded, meaning infinite energy. We don't have infinite energy. We have tendency to go to infinite energy and we call those explosions. You do not want your batteries, right, or any other fuel source, energy source, to have a divergent, right, function that describes it, right? Because at that point you are actually designing a bomb. So for engineering, if you go into any of these fields where you are designing stuff, your integrals, improper integrals, and all of your stuff that you do with power series, especially electrical engineers, guys, you are all going to look into convergent ones. And if you spot divergence, you immediately have to correct either the design, the thinking, maybe you made a mistake in calculations. You know, there are things that you have to worry about. So now we understand that, and I'm going to take a look real quick here at some ideas in terms of combining power series and splitting power series, which are the same rules that you guys had earlier for series. So if I have a power series that has, let's say, different coefficients, so C n m plus or minus dm times the power series x to the now let's do first so cn xn, let's do this first. So that's going to be summation of cn x to the n plus summation dn x to the n, or a minus depending on which one you have. You can start at 0 if you want, or 1 or 7. This one over here allows you to split series, so we can split PS power series if we need to. Remember the favorite NGIT problems, right? When we separated, as same works, same here. Another one is multiplication by power. Pay attention, differential equations on all of these. If you have a power series and then there is some kind of x to the p in front, have this for Euler's equations and stuff like that. you can bring this one inside, and this formula works backwards and forwards. So n plus p. This is a basic algebraic idea. It's just that you will sometimes have to kick x outside, sometimes have to bring it in, depending on what type of a problem you have in diffq. This rule, there's a star right there. Well, all of these rules are insanely important for diffq, but this one. And the one that we need for this class for 11.4 and your final exam is composition. You remember the composition f of g of x, right? Also known as a fog. Well, this one allows us to make a composition, and I'm just going to write it as a composition. So here's your Cn, right? Standard 0 to infinity Cn. And now I'm going to have f of x to the n. I'm going to put the blood red over here around this one. Now, you might say, whatever. 11.4, looking forward. Integral of e to the x squared dx. You can just cry, right? Go through the whole Kleenex box. You are missing an x in front for u sub. You can't do by parts. There is nothing you can do. There is something you can do in Calc 3, but there is nothing you can do right now. Now, power series is going to make a joke out of this. What do we know? You know your power series for e to the x. It's 1 plus x squared over 2 plus x cubed over 6 plus dot, 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 dot. Yeah. And you know what you're going to do now? You're going to go and you're going to say e to the x squared is equal to 1 plus x squared plus x squared, which will become, when you square it, plus, do you see what's going on over here? And now you're going to work this polynomial out, and you're going to integrate that. I know, right? And that's your 11.4. This is why this formula is so damn important, because you know your power series of E was given by this, and then instead of having an x there, you're going to put x squared, or you're going to put x cubed, or you're going to put 1 over x, or you're going to put a sine x there, right? Whatever is there in a problem. If you can't integrate with the regular rules that you know, power series is always there, just like one punch done. Now, obviously, knowing power series and how to combine. So 11.4 is going to introduce and use this. So you must know this to go through 11.4. The previous two sections, the previous two formulas, right, these two, they're going to be there in differential equations, both of them, right? So I'm going to put these two stars over here. I'm going to put a star. Need for diffq. That way, you know that, I mean, your chapter 3. If you don't know these two formulas, you won't be able to do any problem in chapter 3. From the first example to the end of the chapter, every problem will have these two, and every problem will have shifting the counter. You remember shifting the counter from? Yes. Mm-hmm. So every problem will have these two formulas and shifting the counter in chapter 3. So you do not want to kill the whole chapter because you don't know those three things. 1, 2, and shift. So we'll deal with that obviously once you take the class. But now we have these things here, and that's it. Bye.